Have you ever gazed at the night sky and pondered the possibility of life beyond our pale blue dot? This is a question that has intrigued us for centuries. As we venture deeper into the cosmos, we come across a fascinating concept: exoplanets, planets that orbit stars outside our solar system. The universe, with its countless galaxies, stars, and planets, is vast beyond our comprehension. Yet, amidst this cosmic sea, we are on a quest to find life. To answer the question, are we alone in the universe? The key to this quest lies in the atmospheres of these distant exoplanets. Their composition can potentially reveal the presence of life, or at least conditions that could support life. Just like a detective searching for clues at a crime scene, astronomers meticulously study these exoplanet atmospheres, hoping to uncover signs of otherworldly life. Now, you might wonder, how do astronomers examine the atmospheres of these distant exoplanets? The journey to studying exoplanet atmospheres begins with the discovery of these exoplanets themselves. But how do we find these distant worlds that are light years away from us? Well, astronomers use a couple of clever methods. The first is known as the transit method. Imagine you're watching a far-off star, and suddenly its light dims slightly before returning to normal. What you've just witnessed is likely an exoplanet passing in front of the star, or transiting. By carefully measuring the amount of light blocked during this transit, astronomers can determine not only the size of the exoplanet but also its orbit. This method has been exceptionally successful and is responsible for most of the exoplanet discoveries to date. Then there's the radial velocity method. This involves observing the subtle dance between a star and its exoplanet. As the exoplanet orbits its star, it tugs the star slightly off-center, causing it to wobble. This wobble affects the star's light, shifting it to slightly bluer or slightly redder wavelengths. By monitoring these shifts, astronomers can infer the presence of an exoplanet and estimate its mass. These two methods combined have unveiled a cosmos teeming with thousands of exoplanets, each with its unique characteristics. Once an exoplanet is discovered, its size, orbit, and mass give us the first clues about its nature. Is it a gas giant like Jupiter or a rocky world like Earth? Does it orbit close to its star or at a distance? These initial insights lay the foundation for the next stage of exploration. It's important to remember that the discovery of an exoplanet is just the beginning. The real excitement lies in what comes next. With the exoplanet identified, the next step is to peek into its atmosphere. And that, dear listeners, is where our story truly begins. Astronomers use a technique called spectroscopy to study the atmospheres of these far-off worlds. Spectroscopy is a powerful tool in the hands of astronomers. It's like a cosmic detective, revealing secrets that are billions of miles away. But how does it work? Think of light as a bundle of different colors, each color corresponding to a different wavelength. When this light passes through an exoplanet's atmosphere, certain wavelengths are absorbed by the different gases present. Now, picture a rainbow, a natural spectrum of light. If we were to look closely at this spectrum after it has passed through an exoplanet's atmosphere, we would notice that some colors, some wavelengths, are missing. These are the wavelengths absorbed by the gases in the atmosphere. By identifying these missing colors, astronomers can determine the chemical makeup of the atmosphere. For instance, if they see that the colors corresponding to the wavelengths absorbed by methane and oxygen are missing, they can infer that these gases are present in the exoplanet's atmosphere. But it's not just about identifying the gases. The relative amounts of these gases can give us clues about the conditions on the planet. For example, a high concentration of oxygen might suggest the presence of photosynthesizing organisms, just like on Earth. Moreover, spectroscopy can also reveal other atmospheric characteristics like temperature and pressure profiles, the presence of clouds, and even the speed at which the planet is rotating. This process is akin to a cosmic jigsaw puzzle. Astronomers piece together the different wavelengths, the different colors, to paint a picture of an exoplanet's atmosphere. Each piece, each color, tells a different part of the story, contributing to a comprehensive understanding of the exoplanet. So the next time you look up at the night sky, remember that those distant points of light are more than just stars. They are windows to other worlds, their secrets being unraveled by the power of spectroscopy. This chemical fingerprint can tell us a lot about the exoplanet's potential for life. So, what are astronomers looking for in these chemical fingerprints? Well, Our quest to understand the universe and the possibility of life beyond Earth hinges on finding certain molecules in the atmospheres of exoplanets. It's like a cosmic game of hide and seek, where we're trying to spot these hidden clues in the vast expanse of the galaxy. One of the key molecules we're looking for is water vapor. Why? Because water is a fundamental ingredient for life as we know it. It's the universal solvent, the medium in which all biochemistry happens. So if we find water vapor in the atmosphere of an exoplanet, it could suggest that the conditions for life might exist there. But water alone isn't enough. We also need to find free oxygen. On Earth, free oxygen is a byproduct of photosynthesis, a process used by plants and certain microorganisms to convert sunlight into energy. So if we detect oxygen in an exoplanet's atmosphere, it could be a telltale sign of biological activity. Yet another molecule of interest is methane. Methane can be produced by geological processes, but on Earth, a significant amount of it is produced by biological sources, like cattle and microbes in wetlands. So finding methane in an exoplanet's atmosphere might also suggest the presence of life. But here's the thing. These molecules, water vapor, oxygen, and methane, they're not definitive proof of life. They're just clues. They tell us that the conditions on those planets might be right for life to exist. We also need to consider the planet's size, its distance from its star, and many other factors before we can start dreaming of alien neighbors. It's a complex puzzle with many pieces, and we're just beginning to assemble it. But the search for these biosignatures is not without its challenges, and we'll delve into some of these challenges in our next scene. For now, let's marvel at how far we've come in our understanding of the universe and how much more there is left to discover. Unraveling the mysteries of distant exoplanets is a complex task fraught with challenges. Studying exoplanet atmospheres is a bit like trying to decipher a book written in a language we barely understand. We're peering billions of miles into space, trying to make sense of faint signals that have traveled for years, if not centuries, to reach us. The sheer scale and distance involved can make this a daunting task. Moreover, our current technology has its limitations. While we've made significant strides in the past couple of decades, we're still working with tools that were not specifically designed for this purpose. Our telescopes, for example, can capture the light from distant stars, but extracting precise information about the planets orbiting those stars is a whole other ballgame. The light we receive is often obscured or distorted, making it challenging to draw accurate conclusions. False positives present another significant hurdle. Sometimes what appears to be the telltale sign of an exoplanet might just be a glitch in our data or a cosmic phenomenon we haven't encountered before. It's a constant process of analysis and reanalysis, always questioning, always verifying. But let's not lose heart. Despite these challenges, the future of exoplanet study is bright and filled with promise. We're living in an era of rapid technological advancement. New telescopes, like the James Webb Space Telescope, promise to revolutionize our understanding of exoplanets. They're designed to peer deeper into space, capture clearer images, and provide us with more reliable data. Furthermore, advancements in artificial intelligence and machine learning are helping us sift through the enormous amounts of data we collect, identifying patterns and signals that might otherwise have gone unnoticed. As these technologies continue to evolve, our ability to study and understand exoplanets will only grow. As we continue to explore the cosmos, who knows what we might find? Perhaps one day we might even discover that we are not alone in the universe.